Um, Hi, everyone. Yeah, as Adam said, I'm Martin O'Reilly, Director of Research Engineering at the Turing, and today I'm going to try and give a bit of a peek behind the curtain as to how sort of LLMs sort of work and how they, we can build around them to get AI agents. There's going to be a bit of interaction, so if you're not on the Menti already, get on. There's a little kind of checking what you know as the first question, but we'll have some audience participation in a bit. And I'm going to talk about sort of three things today. I'm going to talk about what an LLM is, sort of how we get an LLM to do coding and reasoning, and how we take a coding and reasoning LLM and turn it into an agent that can sort of do things on our behalf in the world. So let's see sort of where we are. Okay. So actually, this is quite a knowledgeable audience, so hopefully there'll be something for you to learn, but it looks like quite a few people would like to know how reasoning works, so hopefully every one of you will take something away from today. So what is an LLM? Well, I think one thing to note is that LLMs are just one part of AI. They're sort of super big in the zeitgeist at the moment, but there's a huge set of other tools and sort of methods available, and often if you've got a particular problem, they might be sort of better suited. And LLMs do sort of one thing, which is predict the next word. But they do it very, very well. And they are very big. So, current models are hundreds of billions of parameters. We're hearing about potential trillion parameter models. Some people are saying Claude Mythos is 10 trillion. That feels a little high, but we'll see. And they are trained on trillions of words, and they sort of handle context windows of sort of hundreds of thousands of words. And even though they're trained to do this one thing, which is predict the next token really, really well, they can do these other things if we do a little bit of extra training. And that's what makes them an example of a foundation model, and I'll talk a little bit more about what that is sort of later. So what I'd like to do is start with a little bit of audience participation to give us a feel for this text completion task ourselves. So if you all get sort of Menti up. Okay, so I'm going to give you the first couple of words in a sentence, and then I would like you to put in what you think the next few words are. So call me. Okay, maybe. Excellent. Let's keep going. Al, Daddy. Okay. Tomorrow. Yeah. Okay. A lot of votes for maybe here. Okay, sexy. Fine. Okay, later, call me back. Okay, lots of phone call sort of related things going on here. Let's see, so maybe we get up to sort of 50 or 60, and then we'll sort of go on to try the next one. Okay, sort of last few seconds if you want to sort of contribute to the crowdsource here. Okay, call me never, call me later, call me baby, call me now, call me back. Okay, so what about it was the best? Of times, time of day, presentation. Thank you very much, whoever that was. Yeah, time. Conference. Yes, I would agree. Day of my life. Food. Yes. Okay. So quite a variety sort of here. Okay. Cool. What about? It was a dark night, dark forest, dark matter. Okay, some physicists in the room. Dark alley, someone's had a traumatic experience recently. Okay, lots of night. Someone's got a dark day. I mean, that you should probably talk to somebody. Okay, all right. And I think there's one or two more. It is a truth bomb. Okay, dilemma. Okay, somebody's got something they're thinking through. Detector. Potion, seeker, ooh, philosophical. Okay, so sort of bomb and seeker still the biggest sort of votes so far. Let's give it a few more seconds, and then we'll sort of move on to what I think should be the final one. 2 households. Okay, so I think we've got one more. Multilingual, excellent. I'm going to assume that one is correct. Cool, lots of division going on here. Two households, one cup. I'm assuming that's the football coming up. Okay, all right. I'm going to race on to the last one, which is once upon a time. All right, let's see how many sort of votes we get here for different things. Once upon a Python, excellent. 2 times, somebody doesn't just want once. In Hollywood, yeah, okay, we got a movie going on here. Okay, so we got a fairly, galaxy far, far away. That will come later. Okay, so once upon a time. Okay, so now we know it's books, right? And what I'd like to do is just do a quick couple again to see, now that we know it's books, are we still thinking Call Me Maybe? Okay, I did not know it was possible to put emojis in. Okay, we should probably just have loads of those. Okay, so Call Me Ishmael. Okay, so this is the first line of Moby Dick, getting much more votes this time. Call Me By Your Name, I think that is another book or a movie. Okay, and moving on to It Was the Best. Someone still sort of remembering a highlight from the weekend. But now that we know it's books, what do we think the next word is? The best of times, exactly. So, the key thing here is with a little bit of extra context, we know it's books, we can do a lot better. And one of the things these models do is get a lot of context, and we'll talk a bit about that. So firstly, let's see how the models do compared to us. So I've got a few models here, mostly generations of GPT, but I started with my Android phone a few years ago, and it got Once Upon a Time. It got the one we all got, but it did terrible at the rest. It was a bit like us, Call Me When You Get Home. Then GPT-3, which is not a chat model, just text completion, sort of came out in June 2020, gets about half of them right. And then you get to 3.5, which is ChatGPT, which is what came out to a big storm in November 2022, and it's getting maybe 2/3 of them right. And ChatGPT-4 sort of gets pretty much all of them right. And you go to ChatGPT-5, and it will refuse to answer most of these because of copyright reasons. But for both the chat models, the interesting thing is if you give it all of them at once in one prompt, it will get all of them right. So again, it's able to leverage that extra context. So how do LLMs do this under the hood? Well, they do this next word prediction, but how did they get good at it? Well, there's a few things that they put together, and some of these existed before, and some of these are the one cool trick that sort of came out in 2017. So they represent the meaning of text, and they do this via word embeddings, which is just a sort of way to turn words into numbers, and those numbers represent sort of locations in high-dimensional space. And the key idea here is to understand words by the words around them. So words of a similar meaning will cluster together in this embedding space, and similar modifications in word meaning should result in similar changes to embeddings. So, sort of man is to woman, it's the same direction vector in feature space as king is to queen. And similarly, if you go and look at verbs, walking to walked, swimming to swam, they're both past tense transformations. And so this is one of the sort of key building blocks that LLMs are based on. It's been around a long time. If you want to sort of Google it, Google word to vec. The other thing that they've done is they've learned how to leverage an awesome amount of training data. So this is internet scale data. These LLMs are trained with a lot of data. So GPT-3 back in 2020 was trained with something like 200 billion tokens, 200 billion words. But modern LLMs are being trained with trillions of words. And the other thing is worth noting with modern LLMs is the first ones were trained broadly on the internet, a bit of Wikipedia, so sort of more curated, and a lot of books, which is why they do quite well on that task that we were just doing. But modern LLMs, even in that pre-training for next word prediction, there's a lot of academic documents, there's a lot of examples of code, and there's a lot of maths. And the key thing here is figuring out how to train on that data without labeling any of it. And the way we do that is we hide some of the words, and we know they exist because they're in the internet data. And then we get the model to predict those words by giving it the words before. And when it gives a prediction, we can tell it whether it's right or wrong and how much, because we know the right answer. And that's what allows you to kind of churn through these billions and trillions of tokens and do this kind of supervised or self-supervised learning. And now we're getting to the bit where the real innovation happened with sort of LLMs, which is how to handle context, the length of context that can be handled and how clever the model is about how it considers that context. So more context is generally more meaning. So when we were doing these, we weren't so good at the first few. When we figured out it was books, we were better. If we got them all at once, we'd probably do better. But let's say we started with bigger sentences. So I won't do a Menti here. I'll just ask you to shout out in the room. Paul went to the bank to deposit a check. Okay, that wasn't really a shout, but we'll see if we can do better on the next one. Paul went to school to sit an exam, exactly. Paul went to the river to catch a fish, exactly. And if we said Paul went to the river to sit on the, we might say bank, and we would be able to tell it was a different bank than the bank he went to put his money into. And the models can do the same. And how do they do this? Well, this is a kind of sketch of what attention sort of looks like. So the animal didn't cross the street because it is kind of where we've got to so far. And the model is looking at it and trying to figure out what the next word is. And so it looks at all of the sort of context behind it, the words that have come before, and it calculates its attention score. And the highest attention score is animal. So it goes, it is animal, it isn't the street. And as a result, it predicts the animal didn't cross the street because it was tired, as opposed to, if it had bound to street, it might say the animal didn't cross the street because it was busy. And so this is the key thing that's going on. And this kind of clever handling of context and then some computational things that make it feasible to handle a very long long amount of context is what makes these models really powerful. And to some extent, if all you got was longer context without being able to be clever about how you interpreted it, you probably wouldn't do anywhere near as well as these models do. And this is this kind of attention kind of mechanism, and how that's implemented computationally is via transformers, and we'll talk about that just now. So, being able to do this kind of processing of large context, and this sort of attention sort of process computationally efficiently is sort of what makes these models feasible in reality. And we just sort of go back to basics for a second. All of these sorts of LLMs are an example of a deep neural network sort of base model. And for those of you who don't know what that is, it's just sort of layers of these nodes, and each sort of layer receives connections from every node beforehand. So if there's a signal coming from the node in the layer before, it gets sort of sent out to all of the nodes in the next layer. And the first layer is the input layer. So for LLMs, that would be your input sentence so far. For an image-based model, it might be the sort of image you want to classify. And the last layer is the output layer. So that's your probability over the next tokens, the next word you're predicting for an LLM, or your probability over classes, cat, dog, lion, if you're trying to sort of classify an image. And then the layers in the middle are the hidden layers, and they do the work. And if you've got more than one hidden layer, you've got a deep neural network. It's not very deep. They're usually deeper than that. But with more than one hidden layer, if you make it wide enough, you can do arbitrary computations of any sort of kind. And sort of what does that look like when you zoom in? Well, each of these sort of neurons, each of these nodes is receiving signals from everything in the previous layer. And the weights of those arrows are kind of how strong that signal is weighted. And you take this weighted sum, and then you pass it through this little blue box, which is a nonlinearity. And that's what means that when you add layers, you add complexity. Because if you don't have that nonlinearity, you could just rewrite the network as a single hidden layer. And so you make this deep enough, you make it wide enough, you give it enough training data, and you can learn sort of really complex mappings between inputs and outputs. So how does that fit into LLMs? Well, you will probably have seen this picture around the internet, and it comes from the Attention is All You Need paper in 2017. And I'm going to sort of go through a little bit about what each of these bits mean. So on the left, you've got something called an encoder. And on the right, you've got something called a decoder. And that bit in the middle, that second attention block, that has the connection from the encoder to the decoder, is sort of a cross-attention thing. And it allows you to connect encoders and decoders together. And in the original paper and this architecture, this is set up for machine translation. So the encoder has the full sentence from the sort of source language that you want to translate from. And the decoder starts predicting what the translation is. And it only sees the tokens generated so far in the source language, in the translation language. But at every time when it's trying to predict what comes next, it can see what it's generated so far in the translation, but it can also see the full text in the source language. And if all we want to do is generate English sentences from English prompts, then we don't need all of these pieces. We can simplify it. We don't need the encoder. We don't need this cross-attention to kind of incorporate the encoder's inputs. And it's kind of more sensible to think about these as input embeddings, as the input sentence we're putting in rather than output embeddings. So it simplifies to something like this. And I'll go through what each of those sort of blocks conceptually does in a minute, but I'm going to first talk through sort of how that works in reality. So this is kind of, you probably sort of recognize how these models work. They're autoregressive. So you take a grey input string a long time ago, you put it in the bottom, and out at the top comes a range of probabilities. The highest one is in. So you grab that, you stick it on the end of the sentence, so the second line, it's now in the grey. You put it through again, and you get A. So each time you're adding the output word to the end of the sentence, and you're making it the new input. And you do this enough times, and you get the opening sentence to Star Wars. And the key thing here is that that whole new input sentence is fed in each time, and the model has no memory of what's gone before. All of the kind of memory of that conversation, of any other interaction you've had, that's all handled by the sort of chat interface, the user interface that you're dealing with. The model itself just gets text in, and it's got no memory of anything it's had before. So what are each of these blocks, and how do they kind of link back to what we talked about before? Well, this block at the bottom, this is the embedding. This is turning those words into sort of vectors that, where similar things are near each other. And it's got this little trick called positional encoding, and it's a thing you add to each of those sort of words so that you can both learn different things about a word depending where it is, because you've got this extra kind of thing that can change. And it also means you can process all the words in that input string in parallel and get sort of speed ups. This bit in the middle is the attention mechanism, so how the model figures out how to weight the input from different parts of the context window. And usually it's sort of thinking, when it's trying to predict the next word, this is a diagonal matrix because we've got a decoder, it can only see the past. So when you're trying to predict the second word, all you've got access to is the first word. When you're trying to predict the third word, you've got access to sort of both the first two words. And sometimes, a lot of the thing that matters most is further back in the context window. Like if you're trying to predict a go, you're sort of looking mostly at time and a little bit, mostly at long and a little bit of time. And then this bit at the top is kind of what lets you learn complex relations between that sort of weighted history and the sort of next word prediction, because the attention block is purely linear. This is what lets you do the sort of complicated mapping between inputs and outputs. And altogether, this gives you a model that's really, really good at predicting the next word, but also turns out to be quite easy to fine-tune with a much, much less computation to do other tasks. And that's what makes it a foundation model. So what's fine-tuning? Well, if we take sort of the original LLMs, when they were only getting the internet and Wikipedia and books, and they weren't getting code and question and answer examples, when you ask it a question, you might not get a sensible answer. You'll get whatever is near, tends to follow that on the internet. So you ask how to fine-tune a model, you might get a lot of other questions about the model. But if you give it some question, and answer examples, of the type of thing you'd like it to do, you can instruction fine-tune it. And what you get is the type of thing we all know and love as chatbots. So how does that fine-tuning work? Well, you've got to start with some sort of known good. So you fine-tune from some human examples. So humans craft some prompts. They craft some high-quality answers. And then you can do supervised fine training. You know what the answer should be. The model makes a prediction from the prompt. You tell the model how wrong it is. And that goes and updates the model weights. And here the model is learning. So when you send the prompt through, it doesn't remember anything. But when you're doing fine-tuning, you're updating the model parameters itself. But that's sort of quite expensive. So there's a way you can sort of scale this and also get a little bit more signal from the bad quality examples by getting the model to generate a bunch of prompts, bunch of different answers to different prompts. And you can grab these prompts once you've done that November 2022 ChatGPT release. Suddenly you've got a lot of users who are generating prompts for you, some of whom have checked the box that says you can use my stuff for training. So you can take those. You don't need to curate any human answers. You get the robot to generate some responses, and then you get humans to rank those responses. And then there's various clever ways you can turn those rankings into updates to the model weights so that they get better at generating the better answers. And originally that would have been called reinforcement learning by human feedback. Nowadays there's a sort of cleverer method called direct preference optimization that lets you sort of avoid training a reward model, but basically it's just a clever way of turning human preferences, rankings or orderings, into a training signal for the LLM. And that's how you would go from the base model to a chat model, and it's also how we do a lot of the other stuff, including reasoning and coding, and we'll come to that now. So how do you go from a chat model to one that can do coding and reasoning? And it turns out that you don't even need to fine-tune it to start with. So some of you probably did this a few years ago yourself. You can do this thing called chain of thought prompting. So you sort of give it an example of the question and answer that you want it to give, and then you sort of give it another question where you don't have the answer. And without chain of thought prompting, you'll get the right structure for the answer, but if it's logic or maths or coding, you might not get the right actual answer. So what you can do is you can augment the answer that you give in the in the prompting example, sort of explaining step by step sort of how to get to the real answer. And then the model does a much better job. So that there is just prompting. You're just changing the text you're putting into the model. You haven't fine-tuned it. You haven't updated any of the model parameters. And it turns out you can do even better than that. You don't even have to give it the reasoning for the particular example. You can just say, I'm not going to give you an example. Here's a logic problem. Here's a maths problem. Let's think step by step. And that's enough to get the model sort of into a space where it's got access to sort of that kind of reasoning trace, and it will sort of, instead of just trying to code and give you an answer straight out of the bat, it will give you this kind of longer explanation that results in the right answer. And that's the type of thing, type of zero-shot prompting. You give it the right sort of structure, you sort of give it this little hint about how to go about it that's not about the answer, and it can figure it out. But really, we'd like to build this into the model capabilities itself. We don't want to kind of leave it down to users to have to kind of prompt the model cleverly. And so we can take that fine-tuning approach we did for chat, and we can do it for reasoning. So you can get all these examples of different types of reasoning, some maths, some common sense reasoning, some data understanding, some domain-specific understanding. And you give it an example question, you give it an example thinking sort of block, and you give it an example answer. And then you do the same fine-tuning. You sort of get some humans to do high-quality prompt answer pairs, do some fine-tuning from that, and then get the fine-tuned model to start generating answers from prompts alone, and use human preferences to kind of tune the model further and scale up. So, how does that look? Well, you've got an internal reasoning sort of example here. User might give a logic problem, put a diamond in a cup, take the cup to the bed, upside down, lift the cup up, put the cup in the fridge, where's the diamond? And early models would have said the diamond's in the fridge because the diamond was in the cup, now the cup's in the fridge. Wouldn't understand sort of that gravity had got in the way when the cup was on the bed. So what you can do is you can give it a thinking trace that kind of explains that. You can give it the answer that you want to present to the user, and then when the model runs, user asks the question. There's this internal reasoning block that's often hidden from the user to start with, but you can often go and see. And then it gives you the example answer, which often includes a little explanation. And we can improve code the same way. So we've got lots of examples of sort of code sort of generation and sort of code correction. So we can grab those, and we can do similar to what we did. But we can do one extra step with code, because code is easy to verify. You can take some code and you can run it. You can check if it gives you the right answer. You can check if it compiles. There's lots of sort of empirical quality signals, correctness signals you can get. And there's similar things like maths and some logic reasoning. You can do the same thing. So you start the same as with fine-tuning for chat and reason. You get some supervised fine-tuning on curated high-quality prompt answer pairs from humans. Then you scale that up with preference learning, where you take the fine-tuned model, generate some outputs, and the humans rank them, and that lets you train the model further. But then you can do this sort of automatic verification, so reinforcement learning with verified rewards, where you get a prompt, the chatbot sort of gets you an example, you put it through your evaluation sort of mechanism, see whether the code gives you the right answer, and you only give a reward if it's correct. You don't give a reward if it's wrong. And then you can generate huge numbers of fully automated kind of examples and reward signals to train the model further. And so together that gets you a model that can code and a model that can reason. So how do you go from that to the agents that we're all playing with at the moment? So the key difference between an LLM and an agent is the LLMs just generate text, right? And agents interact with the world. So we need to figure out how to get the agents to sort of interact with the world. And it turns out, again, that we could do this kind of before the full-on agents we've got nowadays. So one example of this is retrieval augmented generation. It was sort of very big some years ago. It's still a key tool sort of nowadays. In in this example, what happens is the user sort of asks a question, and then the chat system intercepts that and goes, I know I've got access to a private knowledge base, a document store, the internet. It goes and sends a query based on the user's prompt, and then it takes the results that come back from that query, and it injects those into the prompt, and then sends that prompt to the LLM. So it all happens prior to the LLM seeing anything, and you get a sort of more sensible answer back because you've given it this extra context. And that sort of looks a bit like this. So you ask the model who's the Prime Minister of the UK, and the model goes, oh, it's Rishi Sunak as of 2024 when I was trained, and that's not right. But you can go and retrieve a list of Prime Ministers, and you can give those to the model. So this bit in blue is the kind of augmented sort of text that goes in from the chat system. You tag the user's original query on the end. You tell it to answer the question using the context below, and it gets it right. But ideally, we'd like, we've got these powerful reasoning models, and we'd like them to figure out when they need to go and find extra information or do extra things. So you can do this fine-tuning for tool calling. And in the same way that we had these sort of little think and answer blocks for reasoning, we can do the same. Here's a training example for tool calling. So you set the tool's persona, you tell it, hey, you're a question answering machine, you've got access to tools, they come in these little description blocks, you give it some tools, and then you tell it how to interpret the answers. They come in these tool output blocks. You give it an example question, and then you say, at this point, I don't want you to answer the user's question, I want you to call the tool. And so that's your training example. And then you do the same thing, you do some human-generated sort of fine-tuning examples, and you get your supervised fine-tuning, then you get your tuned model to generate more, and you do the preference thing, and you get sort of better performance. And so what does that look like once you've got the model? Well, you say, look, you've got access to the following tools. So the blue is the chat system. You can search the web. The user goes, hey, which team's got promoted to the premiership this year? It's a reasoning model. It does some internal dialogue to go, this is probably the English Premier League. This year is the 25-26 season. That's finished, so we know what the promotions are. I probably need to go and Google something. And then it says to the chat system, hi, please could you send this query to this tool? The chat system goes and does that, however it wants to, grabs the information from the internet, formats it in the result the LLM expects for tool output. The LLM then uses that as its input in the same way as with RAG and goes, okay, so these 3 teams got promoted. I'll provide the answer to the user. And it says, these teams got promoted, and this is the reason they did. And so that's an example of the model being able to choose when it wants to reach out and combining this reasoning with this sort of ability to ask the chat harness to call some stuff. And so for the user, it looks like this. You ask some stuff. You get this block that's usually hidden, which is the output of the tool. You get this block that's usually hidden, which is the internal reasoning, and then you get the answer to the user. So putting all that together, a modern LLM that's capable of sort of tool calling and reasoning and being good at code has this kind of pre-training stage, which for the model that I'm sort of picking up here as the example was split into 3. And this whole first bit is self-supervised learning. Mask some words from the big corpus of text we've got, try and predict what those are, look up the answers and give the training signal. And it's a lot of text, right? So it's, for Olmo, it was 4.5 trillion words from the internet, 800 billion sort of science words from papers, 500 billion tokens from code examples, and a decent amount of maths. Then it does this thing called mid-training. So, you saw right at the beginning that sort of the pre-training now includes kind of a lot of mathsy and science examples. So they give more and more examples here, including some Q&A. So now if you take a base model, it does a pretty good job at chat. It doesn't often know when to finish, but it's got that kind of format right. And then there's some extra stuff to handle really long context. You give it full documents and things like that. And then these last bits are about how you get sort of reasoning, coding, and tool use. So you do some supervised fine-tuning, human-curated sort of prompts and answers. But you can see those are much, much smaller. You've got trillions of tokens on the left, billions in mid-training, and sort of hundreds of thousands in the supervised fine-tuning. And then for the preference learning, you can get away with sort of fewer again, because you're generating lots of examples from each of the prompts. And the humans are judging how good those are. And then you've got the reinforcement learning by verified rewards, for the types of things like code and maths that you can kind of programmatically verify. And there's a little sort of extra stuff around safety in chat that gets included because you don't want it to forget how to do those important things. And that's what gets you this chat reasoning, coding, tool calling LLM. So, thinking about how the LLM and the tooling around it kind of relate to each other, sort of how do you go from an LLM to a modern chatbot? Well, you take this LLM that's kind of trained with reasoning, code generation, tool calling, and then you have this sort of chatbot software, which is sort of like the chat harness. And it handles all the talk with the user, it handles multi-turn conversation, it takes the user inputs, it displays the outputs, it does all that fancy formatting around internal reasoning and tool calling. It handles the context. The model has no memory of what's come before, even in the previous conversation turn. So the chatbot decides, what context to re-inject. It can do sort of clever context pruning, context compaction to sort of make sure that the most relevant stuff is going in. It knows the tool definitions and skills, so it can tell the model sort of when it can call other things. And if you want the model to remember things from conversation to conversation, it also does the memory. And then it also handles the tool use. So it will, when it gets one of these kind of tool calls, it will go, well, is that a tool I can use? Right, I'll send it out, I'll get the results back, I'll format them the right way for the model. So again, the key thing here is that all of the communication between the harness and the LLM is pure text. Right? The model is generating these tokens, these words that say, I would like to call a tool, but it's the harness around it that's doing the actual tool calling and what manages the rest of things like the context and the user interaction. So how do you go from that chatbot to the type of agent that people have been talking about all weekend? So again, you start with this kind of clever LLM. You take a sort of slightly clever agent harness, and the key thing that changes here is the interaction with the user. Rather than having this interactive, multi-turn conversation between the users and the machines, where you might say, write me this function, no, I didn't want it to be like that, could you make it like this? The sort of agent gets to do this sort of think, act, observe loop. And the brain of the agent is still the LLM, but the harness deals with all the interaction with the world. So it might sort of do some internal reasoning, decide to call a tool, observe the outputs of the tool, decide whether it's got enough to do the answer, might spit out some code, might ask something to test it, might come back and do something else. And again, the agent is doing all of the stuff that interacts with the world or your computer. So it's doing this context management, even though the LLM is doing lots of clever reasoning about how to solve this problem and is acting very agentically, it can't actually remember anything. So it's just whatever you put in is what decides what comes out in that turn. But here the sort of agent harness is having lots and lots of turns between every callback to the user. It can do local file access, and so for context management, if we were doing coding, the type of thing there might be a kind of summary of your code repository, the documentation, the kind of dev guide, local coding conventions. Your file access would be sort of reading and writing the code that you want to change, updating documentation. Local tool use could be running some code, seeing the example, running some local tests, using Git to sort of do version control. Remote tool use could be calling up to GitHub to open a pull request, to run some sort of continuous integration testing. And then modern agents can do sort of task decomposition themselves. You go back a year or so, and we were doing a lot of that. The human would have been decomposing the task, but now you can give them fairly big tasks. Like one of the actions an agent can choose to take is to spin off a sub-agent, brief it on what to do, and this whole loop happens again, at a smaller scale. And so maybe those agents are doing function generation, testing, documentation summarization, parallelization of work. So key takeaways, LLMs made possible by huge amounts of data from the internet and increasingly curated sources for things like coding and reasoning. Only possible because of this fully automated pre-training via self-supervised learning. And there's this one weird trick, this sort of ability to cleverly handle big context, both computationally and in terms of this structured attention, that kind of makes them able to generate these kind of very, very fluent sort of text. And if you want to sort of get these models reasoning, you train them for internal reasoning using these think and answer sort of blocks. You do this supervised tuning where humans provide good quality questions and answers. And then you do this preference learning to scale up, where you can sort of take rankings of unknown quality outputs from the machine. Humans can say, I like A over B, and that turns into a training signal. For agents, you need them to act in the world, so you need tool calling. Again, you just use these tool tags. It's just a special token, for the text completion as far as the LLM's concerned. But there's this sort of agent or clever chatbot wrapper around that does the actual tool calling. You add context management, file and tool access. And then, with modern agents, you have this complex multi-step agent turns with tool calling and reasoning. So there was a bit of a whistle-stop tour. I hope you all took away something that you didn't know before or some additional insight. If you want the slides, this link that's been at the bottom of most of the pages will get you there, and you can download them now. If you'd like to learn more about the Turing and the research engineering work there, then click the QR code in green above the chameleon. And I'm sort of new to the Pydata community, but I've been sort of very active in the Society of Research Software Engineering, which is a sort of big community for folk doing software engineering, data science, and infrastructure engineering in a research context, both in academia and in industry. So if you want to learn more about the society and the community there, please click the pink link. And we've got a conference coming up in September, RSECon, that you'd all be very welcome at. And with that, I'll open up for questions.